Hello, everyone. I am Nirmal Malapaka. I'm a visualization developer.
Hello, everyone.
And welcome to another session on visualization.
Hello,
everyone. Today, I will talk about this page, which showcases new and updated features in core visualization. So first, I'll talk a little bit about the structure of this page, and then I'll walk you through some of the more interesting examples. So core visualization is a set of features that cut across multiple visualizations, both scientific and charting. And so there are basically two aspects to core visualization features. One is the framework aspect of it. And we are continually working on the frameworks for releases of the Wolfram language. And then there is a coverage aspect in which we add more functions to take advantage of the features offered by these frameworks. So on this page today, we will look at three main sets of features. The first one is scaling functions, which is covered by the first row of examples. And then the next two rows show off examples of our new framework on uncertainty visualization. Then we'll take a look at updates and new features that we've added to plot layouts, where we can visualize plots with different layouts. And then finally, we have a row of examples, which are applications, which use the features to construct real-world examples. Okay, so let's get started with scaling functions. So scaling functions have been in the language for a while now. We started introducing scaling functions around version 8 of Mathematica, and we've used internally the scaling function framework to release plots that use some specialized scaling around version 9. And then worked on it on the framework for a bit and released scaling functions for the list plot family of functions, the data family of functions, around version 10. So if we look at list plot and look at an example like that, we can add scaling functions to that, and that will scale the data. And as you can see from the y-axis labels, that the data is scaled, and we're using the log scale here. So that's been in the Wolfram language for a while. And then in subsequent versions, we extended the framework to be able to deal with symbolic plots. And so we can also do plot and similar thing. We add scaling functions option, and you can see that the function is scaled, and the y-axis ticks reflect the log scaling. So this time around, what we've done is we've worked on both the framework as well as the coverage aspects of scaling functions, and we've introduced scaling functions for plot 3D. So this page shows off the how to use scaling functions for plot 3D. So if we take that input, so we have a 3D plot that we're plotting here, and we're scaling it using log scale on it, and you can see that the function is scaled. And on the z-axis, you can see the ticks that show the log scaling. We can, of course, give it a list, give scaling functions a list so that we can scale the different dimensions of the plot. So if you give it a list like this with log scaling as the first argument of the list, then we are able to scale. We're able to scale the x-axis So if we exaggerate that a little bit, on the x side, you can see that the x-axis is being log scaled. So yeah, so that's what this page shows. We have plot 3D with log scaling on the z-axis, the x-axis, and scaled on all 3 dimensions. And the last example shows you that we can do scaling, and what the scaling functions do is that they will take any visual element in the plot. So in this case, we have a mesh, and if we apply mesh functions, you can see that the mesh is being scaled automatically. Not only are we scaling the function, but every visual element that we see in the plot that lives in this scale space will automatically get scaled. So that's the first example in scaling functions. I'm going to skip over this next one, which essentially shows a similar thing, but with the density plot and contour plot. So yeah, we have support for scaling functions for density and contour plots as well in this version. The next one is discrete plot. So this is another new plot that we added for to be able to take advantage of scaling functions, and we had to actually extend the framework to support discrete plot because it's a little bit of a different plot in the sense that will take a symbolic input, but the output is discrete. So I think it was full. So if you have a discrete plot like this, and we're plotting the greatest common divisors on a log scale, and you can see that there is scaling happening on the z-axis. Similarly to what I showed you with plot 3D, we can apply scaling in different directions. And if we do, let's say, for the x scale, you can see that not only is the data being scaled, but you can see the visual elements like extents in this case are being scaled along the x-axis. And the last example in scaling functions uses list point plot 3D. This is a data plot, and we've added this to use scaling functions. And this is a nice application example where we are plotting the mass, the radius, and the distance from Earth of the 25 nearest stars. And this example is nice in that it also shows how different frameworks sort of talk to each other. So if we take this example and if we remove the scaling functions, then we can see that the plot has stars basically clustered around the lighter end of the weight spectrum. And so the labeling framework sees that there is not enough space for it to create labels without running into each other. So it doesn't create labels. They're still there as as tooltips. But now once we start adding scaling functions, and let's say we just add it to the x-axis here, it now creates, I think maybe I did something here. If I add it to the x-axis, it'll create a little more space on the x-axis, and you'll see labels start showing up. And the plot itself that I showed you earlier, which has scaling on the x and y axis, so it creates more space, and you'll see more labels showing up. And the labels, of course, live in the scaled space. So that's nice about this example. So moving on to uncertainty visualization. This is a new framework that we added for this version. If you haven't watched the session on uncertainty that was presented by Jose Martin Garcia, I would encourage you to do that. I believe it's on the Wolfram Twitch page. You should be able to look at the recording for that. But I'll give you just a brief introduction to that. So we now have around as a language feature, core language feature for us to express uncertainties in the Wolfram language. So if we have a number like that, then you can see that this is expresses an uncertainty. So there's an uncertainty of 0.1 attached to the number. And so ultimately, we will be able to do everything that we can do with numbers in the system with uncertain numbers. And currently, we are also able to do, for example, quantity is supported. So the quantity of that, we supported. So we'll get a uncertain quantity. And this will come in handy when we look at the application examples for uncertainty. Another way to look at it is that this is an uncertain number, which is normally distributed with a mean of 5.6 and a standard deviation of 0.1. And so we can visualize, traditionally these sorts of uncertainties are visualized as bars with fences on both ends. And so that's what our system does as well. So if we take a look at bar chart, for example, the number is represented obviously as the yellow bar, and then the uncertainty is represented as a bar sitting on top of the bars with fences. So let's briefly take a look at how different plots deal with uncertainties. Let's start with listblot. And this example shows how there are different kinds of uncertainties and how listblot deals with them. So if we take a look at this example here, this is a straight symmetric uncertainty. So it has similar uncertainty on both the negative and positive side. And so this plot understands that. And if we plot it, we'll get symmetric uncertainty bars drawn on top of the points. The second example shows an asymmetric uncertainty. So here we have the uncertainty where the negative and the positive uncertainties are different. And again, if we plot that, we'll see a true reflection of those uncertainties in listblot. And finally, we have in this example, we have uncertainties in both the x and y directions. So if we take a look at one of these guys, and you can see that we have an uncertain x coordinate and an uncertain y coordinate. And so when we plot that, we're able to generate uncertainty bars in both the x and the y directions. Okay, so this example shows list log plot using uncertainties. So this is again one of those examples where there are two frameworks that are interacting. We have the uncertainty framework that goes ahead and draws the bars, and then we have the scaling functions framework that knows to scale not just the points on the plot, but also the uncertainty bars. And so in this example, you can see the uncertainty is getting smaller as we go up in the y scale, because it's being log scaled. We have coverage for uncertainties in almost all of the 2D data plots. And so here's an example of dateless plot using uncertainties. The first example shows just regular bars on the data. And second example shows the uncertainty being represented as a band. And so this is probably a good place to talk about the option that we have. So it's a good place to talk about the option that we have. We introduced this new option of interval markers. And so if we look at interval markers, interval markers can take a bunch of named specifications. And so we have fences where we draw the bar with fences on both the ends. We have bars which get rid of the fences. It's just a straight bar. We have points where we have points at the ends of the uncertainty bar. And then we have ellipses and bands. So ellipses come in handy when you have uncertainties in both the x and y directions. We'll take a look at an example of that. And bands is essentially the example that we are taking a look at now here, where successive uncertainties are joined together and you get a band of uncertainties. So that's a good introduction to jump into the next row of examples on uncertainties. And I guess I'll quickly go through this because we have covered most of these in the previous example. But I'll talk a little bit about the different kinds of uncertainties that we have. So we've had intervals in the Wolfram language for a while. And so here's an example of number line plot with intervals. And so the cool thing is here now we can use around as well. So if you can generate around like that, you can see that we can do intervals as well as around, and the around will show you that mean point. And yeah, so we looked at these two examples, look like the y uncertainties and the x and y, the two-dimensional uncertainties. And here's an example of vector around. So vector around is function that we use for correlated uncertainties. And so we have a way to plot correlated uncertainties. So maybe I can show you a little bit of an example. So when you have, let's see, let me get this example. And so here is a list plot of vector around. So vector around takes the point around which you have an uncertainty, and then it takes a correlation matrix. So here we have a point with an x and y uncertainty, and then we have a correlation factor A. And if we change the correlation factor A from negatively correlated to zero correlation to positive correlation, you can see how we represent vector arounds in list plot, and that's how we can visualize correlated uncertainties. And so that's what this example about here shows. You have a bunch of correlated uncertainties, and they show up as ellipses. And so here's examples with using different kinds of interval markers that I showed you earlier. So this one uses automatic, or by default we use fences. And this one explicitly asks for bars, so we get rid of the caps, the end caps, and we get bars for uncertainties. And then we also have a new option that with which we can customize uncertainty, the style of the uncertainties, that is called interval marker style. And so we have different ways to to specify style for these interval markers. And so in this case, we're using interval marker style gray, and I also use interval marker style red on this example for vector round. And this is yet another example of error bands. So we're again using interval marker option to specify that we want to use bands. And so we get bands. And another nice thing about this is that we have quantity in this example. So you're able to generate nice plot with quantities, even though not sure. So maybe we have to turn on frame label to be able to see those units. And so on the y-axis, you can see we are actually plotting dollars, the price in the data. So that's, I think that's the end of uncertainties. So one more. Right, so this is the last example for uncertainties, where you can see that we're using ellipses. And this comes in handy not just for the correlated uncertainties, but also when you have uncertainties in X and Y direction, and you can then visualize a sort of an area of uncertainty if you use interval markers as ellipses. So I guess I will stop there, and I'll hand over now to Brett Champion, who will talk about the updates to layouts and the application examples that we have. Thank you.
And so going from version 11 to version 12, we've added more functionality in terms of layouts for some of the visualization functions, especially in the list line plot family. And so there we go. Here is sort of our intro example of, I forget if we added this in 11.2 or 11.3, of having stacked layouts within listplot and date listplot, and even added a couple of specialized functions for that in terms of stacked date listplot and stacked listplot. So we're going to look at this example using stacked date listplot. So here we have several years worth of data for power sources of energy in the US. And so we have about 32 years worth of data. And the stacked in this sense is an accumulated thing. So we have our values, we sort of have our baseline curve of corresponding to fossil fuels, so coal and natural gas and that sort of thing. And then we have the energy coming from hydro, which is mostly in the form of long established dams, and that quantity is added on top of our baseline curve. And then we have nuclear and solar and wind. And this data stopped in 2012, and after that, wind and solar, I'm sure, would have made sort of a much bigger jump in things. And so what this allows us to do is to see this data as an accumulated thing, to allow us to see sort of what fraction of things are coming from what sources. And so I can even change it within stacked date list plot to, layout goes to a percentile approach, which then really allows us to see the fractions in an even different way. Oh, I see the plot range is getting clipped there. So it's not going all the way down to 0. I was wondering why fossil fuels was so low. I might take a look at that later. Let's see. But so anyway, with the percentile layout, then everything is normalized so that the total amounts are all 100%, and we look at sort of the actual fractions. And there you can sort of really see the start of the boom in wind farms in the US and wind as an energy source. And as Nirmal was talking about sort of frameworks and sort of having everything work together, then this also works with scaling functions. So I can do this with a log scale on the quantities. It ends up looking mostly about the same as this original plot because we don't really have any order of magnitude changes between the min and the low and the high, and so it shifts a little bit, and you can sort of see that the difference from 2 to 2.5 is a different visual scale than from 3.5 to 4. If you had an energy source that just completely took off, it might show up a little bit better on the log scale. And so the other thing is that while we added stacked list plot and stacked state list plot as built-in functions, these are also available within the normal list plot. So if I'm going to use list line plot, and it does mostly the same things. The main difference is that with the specialized functions, we were able to automate a few behaviors that are otherwise a little bit cumbersome to configure. So that's just a normal list line plot. It helps if I enable the stacked. Actually, let's just state list plot so we get the ticks right. And so the big difference that we've sort of automated in the named function is enabling sort of this filling between curves and all the way and the first curve down to the axis in an automated way. And so so we've added these stacked and percentile layouts to list plot, list line plot, date list plot, even the step plots, so date list step plot and list step plot support those. So sort of that whole family, including the log, the list log plots, that sort of thing. And a lot of that's just sort of leveraging things going through the same core functionality with different options and whatnot. But it makes it sort of really flexible and easy to use. So there we go. The other layouts that we added for version 12, and this is, I consider sort of beginning days for this approach. We're still feeling our way out a little, feeling our way about things a little bit and figuring out exactly how this is going to work, is creating a gridded layout out of a single function. So here we have sort of the 4 biggest cell phone companies in the US, and we look at their stock prices over the past couple of years. And then we, from within a single column list line plot, we say that we want a column layout and we get them as separate curves. And so I'm going to copy these over to my notebook as well. Yeah, let's take up here just so I can stack. So that takes a little bit of time. And so then we get our 4 separate plots. There's a couple things I want to point out about this sort of layout. So one is that in this layout, all 4 of these plots have the same scale on the y-axis. I mean, obviously they have the same scale on the x-axis, being the dates. But it's also the same on the y-axis. It's going from 0 to about 70 something probably. And the ticks are shown a little bit differently, and I think that's especially one area where we're going to be iterating a little bit to get things sort of continually improving. But I mean, you can make honest comparisons between these plots in terms of how high they are and how fast things are growing, or how much they're changing, or how volatile the values are. And so, and so if you have multiple data sets that are sort of you do say date list plot, and they're just sort of all on top of each other and sort of hard to look at, it may be that sort of a column layout is a more useful approach. Just a second. Come on. And let's see. And so one thing that I sort of wanted to mention with this plot layout goes to column is that for the most part, how the options are going to work is that they're applied per element in this column, or per element in a grid. So you can see that I have aspect ratio set to 1/3 here, for example, and that's giving me an aspect ratio for each of these. If I add, say, plot style goes to red, or actually let's make it even more clear. Red, blue, green, purple, then all of these plots are going to be purple. Instead of having one that's red and one that's blue and one that's green and one that's purple. It's using the same style for all of them. And then the question is, why is it purple and not red? And the reason for that is, sort of historical behavior on, dating back to probably version 1 of Mathematica, of how a list of styles is handled within the plotting function. So if we do plot sine of x goes from 0 to 10, and we add our plot style, then this is seen as one style that's sort of encapsulated in a list. Modern day, I would prefer to use directive for this, and just to sort of make it sort of clearer what's happening, we'll have this as a dashed thin purple line, and thin was maybe too thin, so we'll go extreme the other way in terms of thickness. And so just something to keep in mind. I mean, there's a few sort of exceptions to this. Most notably is sort of the plot labels option here, where it's sort of important for the labeling that we have a way of identifying each of these curves. And so the labels in this case by default are sort of being put at the top of each of these panels with what the identifier for that curve is. And so we have not just the column layout, we also have sort of a flexible gridding layout. I'm going to use a slightly different data set for that one. So let's not paste that there. Let's paste that there. So here we have a bunch of statistics for cars, which I suppose are technically maybe considered vintage cars at this point, being more than 25 years old. And so, depending on the classification on the size of the car, I forget exactly what our variables are. Looks like maybe a mileage thing and maybe something else, maybe a price or something. Seems a little bit low for a price. I suppose I could actually look at the example this came from. Weight in miles per gallon. For a bunch of cars, and so then we can say, plot layout goes to column, comma 2, and this is going to give us 2 columns, and so if we do that, we sort of get what, and it filled that sort of going down by column first. So small, mid-size, compact corresponds to the first 3 things in this association of data. I can change it to 3 columns and 2 rows. I can change it to 4 columns, in which case we then get sort of a ragged array of things. But it still will sort of fill things out as best it can. And so that's sort of the generalization for that. These layouts are, again, supported for most of the things in the list plot family: list plot, list line plot, date list plot. I think the exception was sort of, which was the exception? The exceptions were probably the stacked plots that we saw a little bit ago, because it sort of becomes pointless in that case to put each of the data sets in their own thing, because then there's not really anything to stack. And so, but sort of as much as possible, where we supported that within that family, and we'll continue to roll this out across the visualization functions in coming versions, which is the general approach that we've taken with a lot of the frameworks, say scaling functions, labeling, for instance, uncertainty support, where we generate the new framework and we sort of hook it up for the most popular functions first, and then roll it out as an iterative process to the less common cases. And the reason for that is that occasionally it's not immediately clear what how the framework should interact with a particular visualization function, or it may not be clear exactly what the algorithm is. We may have to do some new fresh development, especially for labeling. Sort of every class of functions we expanded out to, there's a new problem to solve in sort of how we're going to automatically label points, how we're going to automatically label curves, regions, surfaces, and so you sort of work out from one function and go on from there. So the next thing that I want to mention is the final element in this row, which is some changes to graphics grid, graphics row, graphics column, so that it's easier to have the frames to have nicely aligned plots. And so this is especially useful in cases where the column and grid layouts we were just looking at won't work for some reason, because you're combining a list plot with a density plot with a date list plot and a histogram or whatnot. So if you can't get there through a single call to list line plot, then you sort of have to take a different approach. And we're trying to sort of make that simpler and involve less friction at the same time. And so here I have 3 plots. I have, well, I mean, in this case, they're all date list plots, but we're looking at 3 different properties in the US. So we're looking at the population, the GDP, and the inflation rate. And so these are very different sorts of things. And so the inflation rate is generally a relatively small number. For the last 20 years, it's been single digits mostly. GDP is in relatively large numbers. Population also large number, hundreds of millions. And so what would happen in the past is if you tried to put these in a grid or a column, it wouldn't necessarily look very good. So I'm going to show you it looking good first because that's the easier case. So if we use, say, graphics column of these plots, then it looks pretty good. I mean, there's a little bit of space that can be tightened up here in those labels, but all the the body of the plots are all the same size, and these edges line up even though the ticks along the along the y-axis are vastly different. And so in general, this is, I think, an improvement to graphics grid and graphics row, graphics column. Again, there's some iteration going on in this. This is being done through a new setting for alignment for these functions. In terms of alignment goes to automatic. The previous version was alignment goes to center. And if you set it back to center, then you will get the old behavior, and you can sort of see how things didn't line up before. And so it ends up with generally a slightly sloppier appearance. That said, sort of some of the things that allow us to have the nicer alignment means that we're going to more effort to measure how much padding there is, how much space we need to, how much space each of these sets of ticks is taking up, and there's a little bit of additional time that takes. If you have 2, 3, 4, 5, a handful of plots, it's probably not going to be too noticeable. If you've got 100 by 100 grid of plots, it's going to be more noticeable. And in those cases, especially if it's something where, say, you don't have ticks at all and everything's the same shape to start with, it may be convenient to switch back to alignment goes to center, and it can be faster in those cases sometimes. And so that's sort of our look at a lot of the new alignment and arrangement sorts of improvements to the visualization systems. And I'm going to look at one more example, which is sort of one of my favorites. I've made these plots a few times over the years. Let's just go back to Corviz and jump straight there. And so this is, sort of looking at how much sunshine does a location get throughout the year. So I'm going to walk through it real quick. So the way that it starts is we just generate the days of a year. So 2019, January 1st through December 31st. And we have a list of, every day of the year. And then we are associating with each date it's noon. And so this in particular is going to sort of give us a handle that is going to allow us to take daylight saving versus standard time into consideration for a really cool effect. And then for each of those days, we get the sunrise and the sunset. So this is being done for Champaign, where Wolfram Research's headquarters are and where Nirmal and I are located. And then with a little bit of work, we're turning that into the date and an amount of time around noon. So we're going to represent noon as 12 hours since midnight. And we're going to have uncertainty as so sunrise is going to be sort of the negative uncertainty before noon, and sunset is going to be the positive uncertainty after noon. And so then we get a bunch of things that look like January 1st, 12 hours plus or minus a couple hundred minutes. And so then we throw it into date list plot with some options, and you get this visual representation of when the sun is theoretically out in Champaign. And so we can see from this that right around the beginning of July was the latest sunset, late in the evening, and the earliest sunrise was a little bit earlier than that, sometime in June. And so somewhere in between there was the day that had the most sunlight for Champaign. And so, just a second. So I have the code that does that. And the first person to put a city into chat, I'm going to run it for that location. We'll see how many people are paying attention. Pittsburgh. Okay. Pittsburgh's going to be boring. It's going to be about the same as Champaign, but so the sunrise and sunset calculations are going to take a little bit longer because it has to actually do some calculations based on position of the sun, and then everything after that is relatively quick. So Pittsburgh, I guess, is a little bit farther north than Champaign, so its latest sunrise or sunset is a bit later than ours. Malmo, Sweden. So if somebody picked somewhere that gets 24 hours of sun, I don't guarantee that the code is set to deal with that in a particularly nice way. And I think the high latitudes take a bit longer for the sunrise and sunset calculations. And I have no idea how sunrises and sunset work. I mean, I'm guessing it's some sort of find root calculation ultimately, but yeah, so it took 26 seconds to get the sunrises compared to about 7 seconds for Pittsburgh. So it'll probably take about 26 seconds again for the sunset. And for everybody who's put in cities, and I'm not going to be able to get to them, by all means, come to this page. You can copy the code out yourself, change Champaign to wherever you want, and give it a shot. Sunset's really taking a while. Okay, so then sunlight, and see how badly the plot blows up on interesting data. It's not that bad. And so, I mean, I suppose the other thing that I wanted to mention that I think is kind of cool about this plot is that I was sort of very careful to have it take the shift in daylight saving time into consideration. And so you can see that Sweden changes at at different times of the year than Champaign does. So we go from saving time to standard time right at the beginning of November, where I think most of Europe is about a week earlier. And they go from standard to saving time much later in March than the US does. The US is sort of very early in March that they make their transition. And so I'm going to go ahead and take a look at see what questions we have in chat. So do scaling functions apply to epilogue? So scaling functions, epilogue. The answer is no, not in that case. And epilogue we sort of view as a very low level tool. And we have an idea, and I think even a design for an option to have epilogue-like behavior that would respect scaling functions, that sort of thing. And it's in the queue, but you sort of have to be prepared to handle sort of arbitrary graphics content in the appropriate way and deal with what happens when somebody asks for a circle centered at a point that isn't, sort of appropriately dimensioned for a particular scaling function. And so there's a lot of corner cases and whatnot that need to be handled carefully and appropriately. But I mean, epilogue, absolutely is, I mean, it would be nice if it did support scaling functions. For backward compatibility, I think we're going to have to add a new option that does a similar sort of thing, because there's too many people that have already transformed epilogues in their log plots and whatnot. And so I think that sort of covers our questions. So I would like to thank everybody for taking about an hour out of your day to come and listen to us. So Thursday is nonlinear finite elements. So that looks like it should be interesting. And thank you again to everybody who joined us, and enjoy the rest of your day. Thank you.